Hello and welcome to Software Engineering CS 470. This will be a first lecture, and so I'll give a little bit of an introduction, and then I'll start to go through chapter number 1. And it's going to be a kind of an interesting class to go through. I think a fairly comprehensive textbook that has a lot of resources that we'll be leveraging. And so Ian Sommerville has his software engineering. This is a 10th edition. And if you go to the editor, there's plenty of information that you'll get from the editor's perspective on this text. But also, if you go to the website, there is lots of information, including the lecture material that I'll be using here. And so there's case studies, video supplements, as well as introductions and giving you a lot of information about what it means to be a software engineer. So I think you'll like that. And it is definitely oriented towards system engineering, which is a term hopefully by the end of the class you'll get a better understanding. And includes a lot of chapters on engineering, resilience, system of systems approaches, and it offers both an introductory and advanced type of perspectives on this. And so here is the contents. And so I will be doing a video lecture for each one of these sections. So for today, I'll be going through the introduction. And so it's based in 4 different groups. And first, we'll have an introduction to software engineering. We'll get into some of the development and system dependencies and security. The third part is then getting into more advanced software engineering topics. And then finally, software management. And I think as a result of this, if you just take this as a holistic approach and then thinking how you can be leveraging each one of these areas, kind of thinking as a tool, these are the various tools in your toolbox that you have at your disposal that might be a helpful thing. So with that, I'm going to go ahead and get into chapter number 1. And like I said, all of these charts are available from Ian Sommerville. So I didn't change them too much, but just linked them all together. And so into one set of overall charts. So this chapter is an introduction. And so the things that we'll cover here is looking at what it means to be doing professional software development. Then what does a software engineering mean as a result? And then it has a section that gets into ethics. And we also talk a lot about faith integration in our courses, and that will dovetail into that quite nicely, as I think you'll see. And there's going to be several case studies that will be introduced. And this is used again and again in the later chapters in the book. So you'll see some of those threads that are developed further. And I know there are some core areas that we're trying to look at in our overall engineering computer science program, including the idea of how to be using CubeSats. And so that will be an application that I'll also be talking about here and there through the lecture material. So in terms of software engineering, the economies of all developed nations are dependent on software. And so computing power and then what you do with that computing capability is something that is commonplace over and over again. More and more systems are software controlled. And you can think of a lot of things being web-based and things being deployed in the cloud. Software engineer is concerned with theories, methods, and tools for professional software development. And so expenditures on software-related efforts represents a significant fraction of the gross national product of all developed countries. So that's an interesting fact to be thinking about. So software costs are dominated by software costs dominate computer systems costs, and the cost of software on a PC are often greater than the hardware costs. And so that's something to be thinking about. And there's various ways of how those costs and things are brought to bear. Software costs are more to maintain than it does to develop. And so that's something to consider. Is like you would think that developing and deploying would be it, but a lot of times these things are operational for quite a long period of time. For systems with a long life, maintaining costs may be several times development costs. Software engineering is concerned with the cost-effective approaches to doing software development. And so what are the things that you want to be aware of in terms of software project failure? And so increasing system complexity, this is an area where there are some potential Achilles heels, if you will, things that could be causing potential areas where you could see failure. So as new software engineering techniques help to build larger, more complex systems, the demands change. Systems have to be built and delivered more quickly, larger than ever complex systems are required, and systems have to have new capabilities that were previously thought to be impossible. And so that's an interesting thread that if you just look at the history of computing, how things have continued to mature, and that's what realistically in the past maybe could only been done in approximation or analytically can be done all together in various applications and software. So if there's a failure to use software engineering methods, this can be an issue. It's fairly easy to write computer programs without using software engineering methods. Many companies have drifted into software development as their products and services have evolved. Do not use software engineering methods in their everyday work. Consequently, their software is often more expensive and less reliable than it should be. So this is one of the things that we're going to be trying to get into this course. It's not just writing software, it's writing good software, it's writing resilient software that is going to be fighting against this trend where you could have failures or issues. And so what does it mean to be doing professional software development? And so here are some examples of frequently asked questions about software engineering. And so what is software? And so this is the computer programming and associated documentation that is part of that. What are the attributes of good software? Good software should deliver the required functionality and performance to the user and should be maintainable, dependable, and usable. What is software engineering? There's various opinions about this, and software engineering is an engineering discipline that is concerned with all aspects of software production. What are the fundamental software engineering activities? You have the software specification, software development, software validation, and software evolution. What is the difference between software engineering and computer science? And so here is an interesting thing that maybe you might think that these are just about the same. And so computer science focuses on theory and fundamentals. Software engineering is concerned with the practicalities of developing and delivering useful software. And so finally, what is the difference between software engineering and system engineering? So we're making the distinction between three areas. System engineering is concerned with all aspects of computer-based system development, including hardware, software, and process engineering, while software engineering is a part of this more general process. And so that may be a way that as we go through the course, you'll get a better understanding of that distinction. More frequently asked questions. What are the key challenges facing software engineering? You have to be dealing with coping with the increased diversity, demands for reduced delivery times, and developing trustworthy software. So you want it done quickly, you want it deployed perfectly, and things like this can be very challenging. What are the costs of software engineering? Roughly 60% of the software costs are development costs and 40% are testing. For custom software, evolution costs will exceed development costs. And so these are some of the things you'll have to be thinking about. How closely does it stand with a off-the-shelf type of product, or how much customization is required? What are the best software engineering techniques and methods? While all software projects have to be professionally managed and developed, different techniques are appropriate for different types of systems. You can think of, like, say, for games, would be developed using a series of prototypes, whereas safety critical control systems require a complete and analyzable specification to develop. And so what is the tolerance for failure or some type of issue? Some things that has to be extremely resilient. So that's one of the things that would come into bear that you'd have to think about. And finally, what differences has the web made to software engineering? So the web cloud-based type of capabilities has led to the availability of software services. Software as a service is a term that you may have heard. The possibility of developing highly distributed service-based systems. Web-based system development has led to important advancements in programming language and software reuse. And sometimes a software-based tool is something that you don't have to constantly update. And so having some type of your resources in a web-based delivery for some applications may not be such a bad idea. In terms of products, we can think of a couple types of groups. First is generic products. And so this would be standalone systems that are marketed and sold by any customer who wishes to buy them. So examples would be PC computer, personal computer software, such as graphic programs, project management tools, CAD software, software for specific markets, such as appointment systems for dentists, et cetera. So that's one type of software. And then customized is where you're working with a customer and you give them what they need that's going to fill that niche. And so this is commissioned by a specific customer to meet your own needs. So you can think of embedded control systems, air traffic control, traffic monitoring systems, et cetera. And I might add, because I mentioned CubeSats before, some space systems also have fairly customized types of systems, but may have some kind of start for some basis and some generic type of routes. So what about dealing with the product specifications and dealing with these two groups again? And so for generic products, the specification of what the software should do is owned by the software developer, and decisions on software changes are made by the developer. So this is you're developing a shrink wrap set of software that's sold in a store, and you've made all those decisions trying to anticipate what the customer would want. And comparison, a customized product, the specification of what the software should do is owned by the customer for the software, and they make the decisions on software changes that are required. So let's just go over some more perspectives and some observations here. What are the essential attributes of good software? So it needs to be maintainable. It needs to have dependability and security, efficiency, and acceptability. So for maintainability, that should be written so that it can evolve to the changing needs of the customers. And so this is a critical attribute because software changes is an inevitable requirement as the business environment changes for whoever's using that software. In terms of dependability and security, software dependency includes a range of characteristics, including reliability, security, and safety. Dependable software should not cause physical or economic damage in the event of system failure. And finally, malicious users should not be able to access or damage the system. And so that's a whole nother area in terms of security and cyber vulnerability issues. In terms of efficiency, software should not make wasteful use of system resources, memory and processor cycles. Efficiency therefore includes responsiveness, processing time, memory utilization, et cetera. And if you have part of your deployment in mobile type of platforms, you're going to see that if you're not using resources efficiently, that the battery is going to drain, and your user community is not going to be very pleased with this type of product. Finally, in terms of acceptability, the software must be acceptable to the type of users for which it is designed. This means that it must be understandable, usable, and compatible with systems that they use. So it needs to fit in with their ecosystem of what they're familiar with. And so that can take a fair amount of work. In terms of some more thoughts on the general roles in system engineering, software engineering is an engineering discipline that is concerned with all aspects of software production, from the early stages of system specification through to maintaining the system after it's gone into use. So it has interesting aspects in terms of, as an engineering discipline, it uses the appropriate theories and methods to solve problems, bearing in mind organizational and financial constraints. And it has to deal with a whole life cycle of the software production. It's not just a technical process of development. The project management and the development of tools, methods, et cetera, have to be considered in the support of the software production. Software engineering is an important thing, and so it's something that to keep in mind. And more individuals and societies rely on advanced software systems. We need to be able to produce reliable and trustworthy systems economically and quickly. And so this may not be intuitive in the beginning, but it's usually cheaper in the long run to use software engineering methods and techniques for software systems rather than just write the program as if it was a personal programming project. For most types of system, the majority of costs are the cost of changing the software after it's gone into use. So remember that. You would think that writing the software up front would be the largest cost driver, but when it's operational, that ends up being a lot more expensive. And a lot of individuals have to be on that part of the process. So let's talk a little bit about the software process activities. And so there's the software specification, software development, software validation, and software evolution. So for the software specification, this is where the customer engineers define the software that is to be produced and the constraints on its operation. The software development is where the software is designed and programmed. So you need to figure out what you're going to do, and then you start to do that development. And after that, the next step is doing the validation. This is where the software is checked to ensure that it is what the customer requires. Does it meet what the specifications has asked for? And finally, if there is some type of evolution that is required, this is where the software is modified to reflect changing customer and market requirements. So you want it to be something that can be agile and adaptable as things go forward. So what are some of the general issues that affect software? First of all, heterogeneity. Increasingly, systems are required to operate in distributed systems across networks that include different types of computer and mobile devices. In terms of business and social change, business and society are changing incredibly quickly as emerging economies develop and new technologies become available. They need to be able to change their existing software and to rapidly develop new ones. So these are the kind of things that you have to be concerned about as you're going through the development and deployment. Security and trust. As software is intertwined with all aspects of our lives, it is essential that we trust that software. And if that trust is lost, it can be very hard, if maybe not even possible, for it to ever to come back. And historically, there have been operating systems and various applications that maybe many people have grown to be reliant on, and then some issues have popped up. And so this is where you can see that it's really important to be using software engineering to ensure that that doesn't happen. Plus, having things be scalable. Software has to be developed across a very wide range of scales, from very small embedded systems, importable or wearable devices, through internet scale, cloud-based systems that serve a global community. And so thus scalability is going to be important. What about diversity? There are many different types of software systems. There is no universal set of software techniques that is applicable to all of them. So multiple fronts in terms of the computing environments, the things that might be available in one platform versus another has to be thought about. Software engineering methods and tools used depend on the type of application being developed, the requirements of the customer, and the background of the development team. Well, what type of applications are there? So you can have standalone applications, you can have interactive transaction-based application, and embedded control systems. And so in terms of a standalone, and these are applications that run on a local computer. So you download and install the software on a device. And so they include all the functionality and do not need to be connected to the network. And so historically, that has been a huge percentage of what would be used on a personal computer. But having this interaction with the internet and cloud is starting to become more popular. In terms of an interactive type of transaction-based applications that execute on a remote computer and are accessible by users from their PCs or terminals. This includes web applications such as e-commerce applications. Maybe you have a banking application that might do that. Other types of services, analytical service of many types that are cloud-based is something that is becoming quite common. And finally, the embedded control systems, the Internet of Things is starting to become very popular. So these are software control systems that are controlled and manage hardware devices. Numerically, they are probably more embedded systems than any other type of system. And so that may be something to be thinking about. A lot of things are getting smart, if you will, with their own type of embedded computing capabilities and control systems. So what type of applications are there? So you can be thinking in terms of batch processing. You can think of entertainment systems or systems for modeling and simulation. So batch. So these are things that you have a lot of things that are loaded up into large aggregations of data that need to be processed. And so then these large number of individual inputs are gone through some computational process and the corresponding outputs are made available. Entertainment systems are another thing that's becoming more popular. Streaming services, for example. So these are systems that are primarily for personal use in which are intended to entertain the user, provide content of one type or another. And finally, systems for modeling and simulation. These are systems that are developed by scientific and engineers to model physical processes, situations, which include many separate interacting objects. Model-based system engineering would be an example of that. And it's also a whole area in terms of the engineering cycle, doing modeling and developing to forecast how a system is going to perform, refine requirements. It actually can be a very important area and actually can be pretty fascinating. Data collection systems is another type of system. So these are systems that collect data from their environment using sensors and of one type or another, and that data is made available for processing. A lot of data analytics is becoming quite popular in just about every area. And so that would be another type of application. And finally, systems of systems. And these are systems that are composed of other software systems. And so you can be aggregating capability together, building one layer of computing that has middleware and ties those things together. And as a result, creates a new application. So those are some of the types of applications that could be developed. But let's talk about now some of the fundamentals. Some fundamental principles apply to all types of software systems. And this is irrespective of the development technique used. And this system should be developed using a managed and understood development process. And of course, different processes are used for different types of software. Dependability and performance are important for all types of systems. Understanding and managing the software specifications requirements. This is something that's important. And then when appropriate, you should reuse software that has already been developed rather than write new software. And we'll be focusing on this more, but once something that has been validated, that is like a gold standard that has been demonstrated, and work with the customer base that they like it, and that can be helpful. So these are just some of the types of fundamentals that you might want to be thinking about as you're developing your software. Internet-based software engineering is becoming more and more popular. Web services of one type of another. A number of different large corporate entities are heavily invested in this. So the web is now a platform for running applications, and organizations are increasingly developing web-based systems rather than local systems. It actually can help in terms of being agnostic about what is the platform that's going to access this data, if it's a mobile device, a tablet, a desktop, a server. All of these things can be running and getting access using standard APIs, getting access to cloud resources. Web services allow application functionality to be accessible over the web, and cloud computing is an approach to provision of computer services where applications run remotely on the cloud. And so you pay for the computational cycles that you're leveraging. And so it's a different type of cost model that exists. You don't have to have a lot of infrastructure that's locally at your business location, but you share those resources with others in a centralized enterprise environment. So web-based software engineering, also, these are complex distributed systems, but the fundamental principles of software engineering are also applicable to them as they are to other types of systems. The fundamental idea of software engineering is applied to web-based software, and in the same way that they are applied to other software systems. In terms of, once again, thinking in terms of some of these in more detail. So for web software engineering, you have software reuse and incremental and agile development. Software reuse is the dominant approach for constructing web-based systems. When building these systems, you think about how you can assemble them from pre-existing software components and systems. And just by aggregating things together in creative ways, you can actually create a new application. In terms of incremental and agile development, how do you start to incrementally expose these to your customer base and let them know that more is coming? Web-based systems should be developed and delivered incrementally. And you can create interesting ways of how you can be, with it almost being seamless to the user, you gradually expose them to more and more capability. Is now generally recognized that it is impractical to specify all the requirements for such systems in advance. And so you can be actually doing some agile development, release a little bit, see how it goes, and then release a little bit more and so forth. Software-oriented systems, this is an area where a lot of work has been going on, and softwares may be implemented using service-oriented software engineering, where the software components are standalone web services. And so we'll talk about software components as we move on later. And then you can have various rich interfaces and with some different standards that have emerged. Interface-developed technologies such as Ajax and HTML5 have emerged that support the creation of rich interfaces with a web browser. And so the web browser definitely has matured and continues to evolve as things go on and on. Well, that's kind of a major section here, and this will now talk about another issue, and this gets into software engineering ethics. We would also want to bring up the faith integration portions of this that I think would be the character foundation of where this would start to fold in. And so just to give an introduction, in terms of software engineering ethics, software engineering involves wider responsibilities than simply the application of technical skills. Software engineers must behave in an honest and ethical, responsible way if they are to be respected as professionals. Ethical behavior is more than simply upholding the law, but it involves following a set of principles that are morally correct. And so people coming to look at a company and wanting to do business with them, they want it to be a predictable experience. They want to see that their data is being protected. There's a lot of different types of things that are out there that would be important. So confidentiality. So engineers must respect confidentiality of their employers, of clients, and irrespective of whether or not a formal confidentiality agreement has been signed. Competence. Engineers should not misrepresent their level of competence. They should not knowingly accept work which is out with their competence. And so within your area of expertise, that's what you should be focusing on. You're typically going to have a lot of expertise in your company that you could leverage and actually get some colleagues to help if you find that yourself in a situation starting out that you need to be getting a little bit of help. Intellectual property, this is one of the key things that a company wants to protect, and there's various ways of how that can come together. So you need to be aware of the local laws governing the use of intellectual properties, of patents, copyright, etc. And so all of that would be part of a legal team, would likely be involved, contracts, etc. And they should be careful to ensure that the intellectual property of employers and clients is protected. Computer misuse. Software engineers should use their technical skills, should not use their technical skills to misuse other people's computers. So computer misuse ranges from relatively trivial, say games or something like that, to extremely serious, infecting systems with viruses and stuff like that. So there are different types of codes of ethics, whether it be, say, an organization like ACM or IEEE. And so they have cooperatives to produce a code of ethics for ethical practices. Members of these organizations sign up to the code of practices when they join. So this set of code contains 8 principles related to behavior, decision made by professionals for its various constituents, whether it be practitioners, educators, managers, supervisors, and policy makers, as well as trainees and students. So what is the rationale for a code of ethics? Computers have a central and growing role in commerce, industry, government, medicine, education, entertainment, society at large. Software engineers are those who contribute by directly participation, or by teaching to the analysis, specification, design, development, certification, maintenance, and testing of software systems. And thus, as a result of these roles in the developing software systems, software engineers have significant opportunities to do good or cause harm. And so that's something you always want to be trying to do. So to produce good, to enable others to do good or cause harm, we want to be helping them to be going in the side of doing good, and we want to be influence others to do good rather than cause harm. So to ensure as much as possible that their efforts will be used for good, software engineers must commit themselves to making software engineering a beneficial and respected profession. So that's kind of a general statement. And here is this code of ethics. And we won't read this in detail, but we'll give a little bit of some perspective. And this information is available in the charts that you can just pause and look at this if you would like to look at it in more detail. So this is basically the software engineering code of ethics and professional practices that all of the professionals that join would sign up to this ethical standard. And so here are the 8 things. So number 1, public software engineers must act consistently with the public interest. So acting in the public interest. Client employer software engineers shall act in a manner that is the best interest of their client's employer, consistent with the public interest. Product software engineers shall ensure that their products and related modifications meet the highest professional standard possible. For judgment, software engineers must maintain integrity and independence in their professional judgment. For management, software engineering managers and leaders shall subscribe to and promote an ethical approach to the management of software development and maintenance. Number 6, professionalism. Software engineers shall advance the integrity and reputation of the profession, consistent with the public interest. In terms of colleagues, number 7, software engineers shall be fair to and supportive of all their colleagues. And number 8, software engineers shall participate in lifelong learning regarding the practice of their profession and shall promote an ethical approach to the practice of the profession. So that gives you an idea of a way of how you're representing your ethical stance and making that public to a variety of individuals. And that could be a discriminator in terms of future contracts for a company, that they say that they can trust the integrity of the company and the resources that they bring to bear for future work. We'll talk about a variety of different applications here, but we can think in also along with these different applications, these case studies with ethical dilemmas. And so if there's a disagreement in principles and the policies of senior management, what should you do? What if your employer acts in an unethical way and releases a safety critical system without finishing the testing of the system? It could have catastrophic results when it's used, and they trusted that company that they're going to provide something that is functional. And what about participation in the development of military weapons, military systems or nuclear systems? Those are some things that might come up. So we're having 4 different types of case studies that are here that we introduce in this chapter, and we'll come back as we move forward. And first is a personal insulin pump, mental health case, patient management system, so a patient management system, a weather station, a wilderness weather station. And so this is involves a space component, which is one of the things within the program that we're developing, looking at CubeSat. And so this may be something worth to pay attention to. And then finally, iLearn is a digital learning environment. So it's a system to support learning in schools and an integrated learning platform. And so that's what we have as we move forward. So we'll just quickly wind through these one at a time. And so you can go back and reference these as in case you want to review them as it comes back, as we review these in future chapters. And so for an insulin pump control system, so this collects data from a blood sugar sensor and calculates the amount of insulin required to be injected as a result of that blood sugar level. So it's the calculation is based on the rate of change of blood sugar levels. This it sends a signal to a micro pump to deliver the correct dose of insulin. So it's not like the patient has to do anything, it automatically does this. And in safety critical system, as low blood sugar, it can lead to brain malfunctioning, coma, and death. High blood sugar levels have long-term consequences such as eye and kidney damage. And so this is the reason why this would be an important type of capability to have. So in terms of the software architecture, and so you have the insulin reservoir, and so this has the ability to do the detection from a sensor. It can be sent an alarm if something goes wrong, and it also can have a delivery system to the patient and having various displays. And finally, you need to have the power so it can maintain its functionality whenever it's called to be used. And we're seeing a lot of these different types of views, and this will be one of the things that we will develop in the class as we go through the specific projects that you will be working on. Here is an activity model of showing you how this would be working. And so you may want to be looking at this in detail. And so first you sense the blood level. It does this computational analysis, and then it finally pumps out the insulin that's required based on what it receives in terms of the blood sugar level. So the essential high-level requirements: the system shall be available to deliver insulin when required. The system shall perform reliably and deliver the correct amount of insulin to counteract the current level of blood sugar. The system must therefore be designed and implemented to ensure that the system always meets these requirements. So that's the first one. And so this second one is a patient management system. And this is for Mentcare, a patient information system for mental health. And so a patient information system, it's used to manage the medical information system about patients suffering from mental health problems and what type of treatments that they have already received. Most mental health patients do not require dedicated hospital treatment, but need to attend specialized clinics regularly when they can meet a doctor who has detailed knowledge of their problems. So they need to have some diagnostics with professionals. And to make it easier for patients to attend, these clinics are not just run in a hospital, they may also be held in local medical practices or community centers. So this application, it's an information system that's intended for use in clinics. And so this is giving you some information about the customer base and the market. It makes use of a centralized database of patients' information, and it can run on a PC, so it may be accessed and used from the sites that do not have secure network connectivity. And the local systems have secure network access. When that is available, they use patient information in the database, and they can download and use local copies of the patient's records when they are disconnected. So it can either operate in a standalone mode and then sync periodically, or it can be online and operate that way, but still have local copies when necessary. So the goal is to generate a management information system that allows health service managers to access performance against local and government targets, to trying to provide medical staff with timely information to support the treatment of patients. And here is an organization of the Mentcare system. You have the clients. They are engaged with the network. That information is shared with the server, and then you have the patient database. And so this gives you a software database architecture perspective. What are some of the key features of the Mentcare system? There's the individual care management, there's the patient monitoring, and then there's administrative reporting. So for the first thing, for the individual care management, the clinicians can create records for patients, edit the information in the system view patient history, etc. The system supports data summaries, so the doctor can quickly learn about the key problems and treatments. There's patient monitoring. The system monitors a record of patients that are involved in treatment and issues warnings if possible problems are detected, so it can see historical trends to see if something is anomalous and that needs to be reported or flagged. And then finally, there can be administrative reporting where the system generates monthly management reports showing the number of patient treatments at each clinic, the number of patients who have entered and left the care system, number of patients sectioned, the drugs prescribed and their costs, et cetera. So this, you can have a lot of business analytics to help you make this cost effective so you can maintain this as a viable capability. What are some of the main concerns? Privacy, of course, would be an extremely important issue. The confidentiality of each individual has to be held, but also authorized medical staff need to have ready access to continue to do the monitoring. In terms of safety, some mental illnesses cause patients to become suicidal or a danger to other people. So these are various safety concerns that would have to be dealt with. And the system must be available when needed. Otherwise, safety may be compromised. And so it needs a high level of reliability. So that's the second one. Now we'll get into a third area. So this is a weather monitoring capability. And so we're focusing on wilderness weather stations. So detect if there's any forest fires, what is the amount of water in the soil. These are could be some things that would be out there. So a government of a country with a large area of wilderness decides to develop several hundred weather stations in remote areas, and then they can deploy them as needed. So these weather stations collect data from a set of instruments that measure temperature and pressures, sunshine, rainfall, wind speed, and wind direction. The weather stations includes a number of instruments that measure weather parameters such as the wind speed and direction, the ground and air temperatures, the barometric pressure, and the rainfall over a 24-hour period. Each of these instruments is controlled by a software system that takes parameter readings periodically and manages the data collected from these instruments. So there's going to be a lot of embedded computing that takes this information, records it, and then makes it available to aggregate that together. So here is the various things that need to be done. And so there's the weather station. There needs to have data management and archiving. And so that's going to be an important system function. And then there's the station maintenance. There's going to be regular maintenance. Maybe some of the sensors need regular refresh, new batteries, hardware refreshes of other types, and what have you. So there's 3 areas here that we'll talk about in more detail, and we were just mentioning in the graphic before. So the weather station system, this is responsible for collecting the weather data. And so that is the most important thing, that you need to have that data before you can do anything else. The data management is how you then get that to a server, and you archive that information, make it available. And then finally, the station maintenance. This is used to communicate by satellite with all wilderness stations to monitor the health of these systems and provide reports of problems. And so there's various types of maintenance. I was talking about operational maintenance, but station management and maintenance is also what they're talking about, is getting to the state of health of each of these so that you could quickly respond as is required. In terms of additional software functionality, you want to monitor the instruments, power, and communication hardware, and report faults to the management system. You want to manage the system power, ensure the batteries are charged whenever the environmental conditions permit, but that generators are shut down in potentially damaging weather conditions such as high winds. So it needs to be responsive to any type of inputs that might affect performance or protect the system, and then support dynamic reconfiguration when parts of the software were replaced with new versions and where backup instruments are switched into the system environment as a result of a system failure. So they're going to have multiple strings of hardware that can be called upon when needed. So that is a 3rd case study, and now we'll just do the last one, and then we'll do a summary. So this is a digital learning environment. A digital learning environment is a framework in which a set of general purpose and specially designed tools for learning may be embedded, plus a set of applications that are geared for the needs of the learners using the system. So Canvas, Blackboard might be examples of ones that you're familiar with, and the tools included in each version of this environment are chosen by the teachers and learners to suit their specific needs. These can be general applications such as spreadsheets, learning management applications, such as virtual learning environment to manage homework, submission, assessments, games, and simulations, various creative ways of having things contribute to the learning process. So this is a service-oriented system. So the system would be able to work with system components that are considered to be replaceable services. You find something you're using now, and say the next term you find something that's a little bit better, and so you could replace a certain module and have that new upgraded service available. It allows the system to be updated incrementally as new services become available. It also makes it possible to rapidly configure the system to create versions of the environment for different groups, such as very young children who cannot read, senior students, etc. So there's a couple things that it would be providing in terms of services. There's the utility services, application services, and configuration services. Utility services provides the basic application independent functionality in which may be used by other services in the system. The application services provide specific applications such as email, conferencing, photo sharing, etc., and access to specific educational content, whether it be scientific films or historical resources. Configuration services are used to adapt the environment with a specific set of application services and do define how services are shared between student teachers and their parents. So this is what the architecture would look like. And we mentioned these different types of services. You have the configuration services, application services, and utility services. And so this is maybe you could think of this in terms of the back end, and then you have the user-facing user interface, graphical graphical user interface, and the application that you would be having that hosted in. So it either could be browser or an application. We already mentioned that, so I don't need to talk about that in detail. And this would be a service integration. That would be a key thing of what it has. And so it uses APIs, application programming interfaces, so it can include third-party vendors. And so it can be just a service platform that has various plugins that can be used. That would be useful and important. And then independent services are services which are simply accessed through a browser interface and operate independently of other services. So that would also be things that would be available. So this information can only be shared with other services through explicit user actions, say copy and paste, reauthorization, etc. Maybe you're going to be watching a YouTube video and you paste a link in there, you post a external website, and if there's things that need to be interacted back and forth, if it's not using some type of integrated service, as we spoke about previously, this would have to take more of a user intervention to bring it back into that learning environment. Okay, well, that is the 4 use cases, and then I'll just have a couple of key points, and then we'll finish up for this introductory lecture. So software engineering is an engineering discipline that is concerned with aspects of software production, all aspects. Essential software production attributes are maintainability, dependability, security, efficiency, and acceptability. The high-level activities of specification, development, validation, and evolution are all parts of the software process, and so you have to keep that in mind. And the fundamental notions of software engineering are universally applicable to all types of system development. So that's the first summary chart. Continuing on with some more key points. There are many different types of system, each requiring appropriate software engineering tools and techniques for their development. The fundamental ideas of software engineering are applicable to all types of software systems. And software engineers have responsibility to the engineering professions and society. They should not simply be concerned with technical issues. Professional societies publish codes of conduct which are set out the standards of behavior expected of their members. And we showed an example of what that would look like. Okay, I think that's the end of this first lecture. Thank you very much and have a good day.